Hello students, I am Dr. Tanmay বিশ্বাস. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is a very interesting topic named as nucleophilic catalysis or nucleophilic catalyst, or sometimes it is considered as covalent catalyst too. Okay, so during today's discussion we shall focus on mechanism. Mainly we shall discuss three types of mechanism and one MCQ. But before going to the details, the MCQ is in front of you. So question is, what is the major product of this reaction? You can see this question here. Four options are provided. I request you student, please read the question carefully, pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words explaining your answer. Don't hesitate whether your answer will be right or wrong, because self-evaluation is essential for improvement. And don't worry, at the end of the discussion you will have the right answer with explanation. Now let's go back to our main topic. What is actually nucleophilic catalyst or nucleophilic catalysis? Means the definition. In nucleophilic catalysis, the catalyst reacts with an electrophilic center of the reactant to form a covalent intermediate in the reaction mechanisms during the reaction. I shall explain everything after some time. So therefore it is sometimes called as covalent catalyst. Why? Because a covalent bond was formed. So a covalent intermediate was formed by covalent bond, and in this case the catalysis involves the lowering of energy of activation for that reaction. So this is common for every catalytic system, because catalyst binds with substrates and reduces the energy of activation for a particular chemical transformation compared to in absence of the catalyst or uncatalyzed reaction. Now let's go back to the main criteria. I believe there is a condition to be a good nucleophilic catalyst. Okay, for that purpose the catalytic nucleophile should be a better nucleophile. The first point, it should react faster with the substrate compared to the other reactant, means the actual nucleophile. Okay, then the reactant, and it is more nucleophilic than the solvent too. That is also an important thing, because sometime during nucleophilic substitution reactions solvents play an important role. So this nucleophilic catalyst is a good nucleophile. It's actually a very effective nucleophile. Okay, and not only that, it must be a better leaving group in the covalent intermediate, because after the nucleophilic attack, means the first step, it produces a covalent intermediate, and that that catalyst must be a good leaving group also. So it is actually a very effective nucleophile as well as it's a good leaving group. Okay, and of course during this catalysis the covalent intermediate should be thermodynamically less stable than that final product under the reaction condition. And actually student, that's the main reason why that intermediate will be converted into the final product. Okay, so let's learn few examples about this process. So example number 1 is hydrolysis of nitrophenyl acetate by base. So if you take this nitrophenyl acetate and keep it in water, the reaction doesn't happen smooth efficiently, but for that purpose equivalent, means stoichiometric amount of alkali needed. Why? Because how the reaction start, alkali do a nucleophilic attack on this ester carbonyl, it opens up, forms tetrahedral intermediate, then it come back and this leaves. Okay, so in this way reaction happens. So after that what it produces this acetic acid plus this nitrophenolate, means 4-nitrophenolate O minus. So after that, means after this what happens, for workup we need to do workup such that this product should be get. Okay, so this is actually I'm talking about the uncatalyzed version, but these reaction could be catalyzed by the use of imidazole. And what happens here, actually this imidazole catalyzes the ester hydrolysis for this 4-nitrophenyl acetate. So the first step is the nucleophilic acyl substitution by imidazole, means this lone pair of this nitrogen lone pair of the imidazole moiety actually act as the nucleophile and it attacks. Okay, by the way, please remember this lone pair of nitrogen is in sp2 hybridized orbital. It is not involved in the aromaticity, that's why it is acting as a nucleophile. So it will open up and it will come back, so this nitrophenolate will leave, so it will be produced. Now So in this case, this N-acetyl-imidazole means this compound is produced. So in the next step, what it will do? So this will undergo further reaction. And by the way, student, you can see that, sir, what is the stabilization of this intermediate, because this nitrogen is carrying a positive charge? Does it have any special stability? Obviously yes. And how it's stabilized? Because of resonance. I mean, this nitrogen also has a lone pair of electron here. So what it does, this lone pair is pushed here and it comes here. So if you draw the canonical form, then how should it look like? So this is the CH3 double bond O, this is the nitrogen, and here this is the double bond. Now this here, and see the positive charge is on this nitrogen. So you can clearly see that, student, that this positive charge is either on this nitrogen or on this nitrogen. So in this way the positive charge is delocalized, and delocalization of this positive charge means stabilization of the positive charge. So that's why this reaction happens smoothly. But there is one but. What do I mean? This N-acetyl-imidazole is not that much stable, as I told, at the condition that it should not be more stable than the product. And that's why what happened, the nucleophile, means in this case the water molecule act as nucleophile, and these water molecule attacks. Okay, so this you can consider that this molecule can attack here, and it can open up, it can come back, and this imidazole will leave, and this imidazole will leave, and ultimately the acid will be produced. Okay, so this is the overall thing. Now why this imidazole leaves? Because remember, this after leaving, this imidazole is a neutral molecule. So that is, since a cationic species converted into a neutral molecule, so that is the reason why it leaves. So you can see this mechanism little better way here. This imidazole attacks and it produces this nitrophenolate part and this N-acetyl-imidazole here. Now in the subsequent stage, it's hydrolyzed by water, fine, produces acetic acid and imidazole itself, as I told some time before, that this is the neutral molecule. A neutral means elimination of a neutral molecule. A neutral molecule is a beta leaving group because charge neutralization. Now interesting part is that, student, this is actually the intermediate of this reaction. Okay, means here there is a covalent bond between, this is the covalent bond. So this is the covalent bond between the reactant and the imidazole moiety, or you can say the catalyst. So that's why this is called as covalent catalysis. Now this intermediate could be trapped. How? By using aniline. And how this happened? This aniline attacks this carbonyl carbon instead of water. So after that, what it does, it opens up this and consequently it leaves. So similar mechanism, it produces the neutral molecule, that is imidazole, and another molecule, that is acetanilide. So that is the proof of this mechanism. Now let's come to the second example, that is nucleophilic catalysis in acetyl nucleophilic substitution. And by the way, the previous example was also belongs to the category of acyl nucleophilic substitution. I'm sorry for the misspelling. So this is acyl nucleophilic substitution, both this one and the previous one, but the previous one falls in another special category, that is ester hydrolysis. Okay, so now let's go to learn this acyl nucleophilic substitution and the use of nucleophilic catalyst. In this case, the nucleophilic catalyst is this one, pyridine, and we know that this pyridine has a lone pair of electron, and this lone pair of electron is in sp2 hybridized orbital. So that's why it can act as nucleophile. And this is, student, actually this molecule is acetic anhydride, and we know acetic anhydride is significantly electron deficient in the carbonyl carbon. So what happens in this case? In this case, the lone pair of nitrogen attacks this carbonyl carbon, it opens up, come back, and it leaves. So one side is acetate anion and another side is, you can see, this cationic species, or in our reaction this is the covalent, means the intermediate. Okay, which have a covalent bond with this catalyst. So here catalyst is imidazole. Now a question may come that, sir, between one acetate versus these two, which one is more reactive? Obviously the intermediate 2. Why? Because in case of acetate, it's actually a negatively charged species, it has resonance, so this carbonyl carbon is not that much electron deficient, so reaction will not happen, or nucleophilic attack will not happen on this acetate moiety. However, the nucleophilic attack will happen on this carbonyl carbon. Why? Because here the carbonyl carbon is attached to this nitrogen, which is carrying a positive charge, and we know that positive charge means deficiency of electron, and that is the reason why it will react in the next step. So in the next step, what will happen? This water molecule will attack with this carbonyl group with its lone pair. So it will first open up, and later on it will come back, and these pyridine will leave. Why? Because this pyridine is now neutral molecule. Okay, this is neutral because previously it was carrying 1 unit of positive charge. So that is the driving force like the previous one, and not only that, during this process it will produce this acetic acid moiety and H plus again. Okay, so this is actually a overall catalysis reaction. So see, in the first step the catalyst means the pyridine was consumed, at the end it is regenerated, so it's actually a truly catalytic process. Okay, so not only this, such kind of reaction is also observed in case of anhydride and alcohol reaction to form an ester, and in this case you can see this is DMAP, or full form dimethyl amino, another final is pyridine. Okay, so this is dimethyl aminoperoxide, this is a pyridine part. Now, so this pyridine part actually act as nucleophile, similar process just I have shown, and ultimately it produces this intermediate which reacts further with alcohol, means alcohol attacks here similar way, and ultimately it produces the ester molecule. Okay, so this is the overall reaction, and in this way it reacts, ester is produced, and after through catalytic process thus it is again generated, and in this way reaction communicates. Not only that, like acetyl chloride RCOCl, if we want to form acetyl chloride to ester RCOOR prime in presence of OR prime, OHR prime, this alcohol, so in that case what is used? Any base like triethylamine or pyridine, etc. In that case this triethylamine also act as a nucleophilic catalyst, and by the way I have already discussed a dedicated lecture where I have shown that the intermediate in between this RCOCl plus TEA could be isolated. I shall provide the link in the description, please visit for better understanding. Now let's come to the third or last category of our today's discussion, that is iodine as nucleophilic catalyst. By the way student, it is not iodine, actual the nucleophilic catalyst is iodide. Sometimes it is pronounced or represented in such a way, but you should understand the reality. So in this case, two types of reaction we shall discuss. So first category is, this is actually alkali or hydroxyl anion reacts with RCl or alkyl chloride. Okay, and this is actually student, please don't go about the bulkness, substitution, everything, just consider this is a primary alkyl chloride, and this is actually an SN2 reaction we are talking about throughout the discussion, and it ultimately produces this alcohol through a SN2 type attack, means you can consider that this alcohol will attack and this Cl will leave, and ultimately it produces chloride ion and alcohol. Okay. Similar, very easy reaction, and this reaction requires heating, and it is generally a slow reaction. Why? Because hydroxyl is first of all not a very good leaving group, and very good nucleophile, and chloride is not a very good leaving group. So that's why reaction is slower, or you can consider this reaction is associated with relatively higher energy of activation. Okay, but these reaction could be carried out under relatively milder condition or faster rate by addition of catalytic amount of iodide, or more specifically if I say potassium iodide. Okay, I shall come after some time. So this potassium iodide and this reaction happens smoothly. Now I shall give you the mechanism in details. Now a question to you. Okay, in this case the potassium iodide versus if I use tetrabutyl ammonium iodide. Okay, so tetrabutyl ammonium iodide, in which case the reaction will be faster. I told that addition of slight amount of Ki increases this rate. Now another question, instead of Ki, if I add quaternary ammonium iodide salt, will the reaction be further faster or slower compared to Ki? So I request you, please write this answer of this question in the comment box, and I am giving you one hints. This is, please try to recall the concept of PTC or phase transfer catalyst. By the way, I have already discussed a dedicated lecture about this phase transfer catalysis. If you have any doubt on this concept, please visit for better understanding. Now let's go to the mechanism, how this reaction actually happening. So first step is one SN2 reaction, an SN2 reaction between this RCl versus iodide. And remember, if you compare this hydroxyl versus iodide, obviously iodide is a good nucleophile. So that's the reason it reacts efficiently. So it will attack here, it will come back, and ultimately it produce this alkyl iodide. Okay, and so this is the first step, and this is the intermediate, this Ri. In the next step, this alkyl iodide is further attacked by alcohol, and it produces alkoxide. OR means hydroxide, and in this way it will produce this alcohol and iodide. So first iodide is consumed and second iodide is regenerated. So this is truly a catalytic process, overall catalytic process, and the second reaction is also a SN2 type reaction. Now in the first reaction, nucleophile was better, iodide, and in the second step, leaving group was better. Okay, leaving group better, because we know that iodide is both a good nucleophile as well as good leaving group. So that makes this iodide eligible for this nucleophilic catalysis reaction. And by the way, student, let me give you the answer of this question just sometime before I asked. The answer is, if you use this quaternary ammonium iodide, then the reaction will be even faster or better. Why? Because potassium iodide is actually an inorganic salt. Its solubility depends on the solvent, organic solvent used for this nucleophilic substitution reaction. But this quaternary ammonium iodide to a tetrabutyl ammonium iodide, it is actually a phase transfer catalyst or PTC. Consequently, what will happen? Actually, it is soluble in both organic as well as inorganic solvent. So that's why, since the reaction is carried out in organic medium, this iodide salt, this quaternary ammonium iodide, is more soluble in the organic reaction medium. That's why reaction is expected to be even faster. Okay, so that is the another concept of the utilization of phase transfer catalyst for any nucleophilic substitution reaction. So please visit the lecture if you have any doubt in understanding. Now a question may come in your mind that, sir, why this two-step reaction is faster than single step reaction? Means single step means the above one and this one, and the two-step means the second one, means this one, nucleophilic catalysis. This is because, student, the first step is associated with higher energy of activation, but the second reaction, although it is associated with two step, but energy of activation is less, because iodine is a good nucleophile, so it's more reactive. Second, iodine is a good leaving group, that's why also it's more reactive. And in overall these two steps, that's why became faster compared to this one individual step. Okay, and if you want to visualize that thing little better way, just look at this RCl plus OH, means alkali, reacts and produce this ROH. So this is the transition state. Remember, this is one step process, so this is SN2 types process, so no intermediate form. In one step it converted into the product alcohol, and this is the energy of activation. So delta EA. Okay, and this left side coordinate is this energy coordinate and the right side is reaction coordinate. Fine. Now let's come to the second and comparison means first one is without nucleophilic catalyst and the second one is with nucleophilic catalyst. What happens? So with nucleophilic catalyst means iodide will react first and it will produce this alkyl iodide intermediate now, and it is an intermediate. It's a relatively stable molecule, not a transition state, because previously this one step process, this is a transition state. So first this intermediate will produce, and second step this intermediate will be converted into the product. How? By reacting with this hydroxide anion or hydroxyl anion. So if you compare, in the first case the energy of activation is delta EA. Now in the second case the energy of activation is delta EB. And please try to understand from this graph just this delta EA is greater than delta EB. So we can understand here clearly that the energy of activation for this nucleophilic catalyst mediated SN2 type of reaction is less, means delta EB less. If the energy of activation less, then reaction will happen in faster rate. So that's the reason why this reaction happens smoothly, or you can consider faster rate, and ultimately in both case this alcohol is produced. Okay, so this is explanation in another way. So in conclusion, what you have learned today, that a very effective nucleophile and a good leaving group is iodide, or you can say imidazole, or you can say this pyridine. Or second, these during this catalysis procedure, means I am talking about this covalent catalysis, two nucleophilic substitution reaction occurs. Just sometime before we have seen in case of iodide minus, first this attack with RCl, second means where it acts as a nucleophile, in the second step it's acting as a leaving group. Now presence of this catalyst improve the overall reaction efficiency by lowering the overall energy of activation for this chemical transformation, and this is called covalent catalysis, as the catalyst forms intermediate with the substrate by a covalent bond. I repeat, it forms a covalent bond. And the final silicon iodine bond is quite weaker due to improper matching of the orbital. What do I mean? Orbital of silicon and orbital of iodine. So compared to silicon oxygen, because silicon oxygen is very stable, because it's first of all oxygen belongs to second row, silicon third row, matching is relatively better. Second, the lone pair of oxygen could be donated to the vacant d orbital of silicon. I repeat, the lone pair of oxygen which is in means 2p orbital could be donated into the energetically accessible vacant d orbital of silicon atom. So whatever sigma bond you are watching here, it actually a sigma bond, but this silicon oxygen bond strength is more compared to a single bond, and that it is actually a partial double bond character. So that is the driving force why silicon iodine bond is converted into silicon oxygen. Now this actually I haven't taught, right now I am going to teach you. So let's come back to the MCQ. What is the major product of this reaction? Now just look at what reagent. So this is a ether molecule, cyclohexyl methyl ether. This is trimethyl silyl iodide. By the way student, previously I guess you have seen many times this trimethyl silyl chloride, or it is named as TMSCl for silyl enol ether preparation. I have already discussed many lectures on this topic. You may visit for better understanding. Now this is a little different. So but property is same, because this silicon center is electrophilic like this TMSCl. So in acetonitrile or MECN is a solvent, and room temperature means how much milder reaction condition it is. So now let's discuss the mechanism. In the first step, what happens? The lone pair of oxygen attacks the silicon center. You may consider this is a SN2 type of reaction, and ultimately iodine is a good leaving group, so it will leave, and as I told, this silicon iodine bond is not that much stronger, so it will leave efficiently, as here the oxygen silicon bond is produced. Point number one. But there is a twist, or there is a but, because The oxygen is carrying a positive charge. Why? Because after this nucleophilic attack, oxygen is carrying this positive charge, and we know oxygen is a very high electronegative atom, and positive charge means, student, deficiency of electron. So deficiency of electron on a highly electronegative atom is not a stabilizing factor. Okay, so in the next step, what happened? This iodide acts as a nucleophile and attacks here. Okay, and it leaves, because iodine is a good nucleophile. Just some time before we have learned. So in this way, what it will produce, sorry, this is not methanol, this is methyl iodide. So it will produce this methyl iodide one side, and another side OSI-Me3. Now in this case, this silicon oxygen bond is stable, as I told some time before, so that's the reason it will produce. So let's come back to our questions. What is the answer? Option D is the right answer. Okay, now a question may come in your mind, sir, water is given, so you can expect that this silyl ether will be hydrolyzed. Student, remember, this is actually an ether, silyl ether. Second, this oxygen silicon bond is stronger, so simple water can't hydrolyze this oxygen silicon bond. So an hydrolysis of oxygen silicon bond, this concept you will understand in the silyl enol ethyl video of mine. I have already uploaded, so please visit for better understanding. Now, so this is, so hydrolysis, further hydrolysis will not be possible. Now if this question is provided in your exam less than 30 seconds, how can you solve? First of all, you need to remember that trimethyl silyl iodide, it's like trimethyl silyl chloride, silicon is electron deficient, so this oxygen lone pair will attack. And by the way, please try to remember recall the concept of trimethyl silyl triplet. Triplet is a good Lewin group, similar like iodide, it's a good Lewin group. So similar thing, so this ether will attack first, and I suggest you please draw the intermediate. What intermediate can produce means this oxygen will have a formal positive charge attached to this silicon. So if you can draw up to this, you can understand in the next step iodide will attack and ultimately produce this SiOMe3. Now why not other option? First of all, it is actually an elimination. Did I provide any base? First of all, OMe is not a CH3 is not a good Lewin group. It can, means if you provide acidic condition or very strong base, then possible, but did I provide any acid or base? This is a trimethyl silyl iodide, no acid or base, so this is not possible. Second, I haven't provided any acid, so ether hydrolysis to corresponding alcohol, not possible. Second, as I told, this SiMe3 cannot be hydrolyzed because the silicon oxygen bond is significantly strong. Now third, iodide, how is possible? Did I provide any HI type of thing? No, so this is also not possible. So option B is the right, option D is the right answer. So this is the end of the discussion. I believe this video may be useful for you. Please write your opinion in the comment box, and if possible, please visit my another channel where I upload global warming and climate change related videos. So thanks for watching. See you in my next video. Bye bye.